basically a question mark in the title, so there will be a lot of questions also, and items for discussion. And I basically want to talk exactly about these three things: climate extremes on the one hand, systemic risks on the other hand that are imposed by that, and then a bit about what artificial intelligence can possibly help with this. I think climate change is, of course, really now common sense, so one doesn't need to lose too many words on that. The more we emit, the higher the global temperatures will go. If you right pictures higher emissions, left pictures lower emissions, and what you can see also is that the warming is not uniform. So a 2-degree warming doesn't mean everywhere it's 2 degrees, but rather, for example, in Europe, it's rather going to be more like 4 degrees, and if we go higher north, it's even much more. So we have latitudinal gradients and gradients between land and ocean. Is something that is already not always so well known, but it's really important. And the other thing that is really important with climate change is that it's often perceived as a warming. But actually, my own opinion is that actually the warming is maybe less important than the changes in the water cycle. And at the same time, it's also more uncertain and more challenging to predict that. But there seems to be some coherence between different metrics and also between different modeling approaches, or between different climate models, where we see that these semi-arid areas, like here, for example, the Mediterranean, which is already quite dry, of course, in summer, as you know, is even becoming drier in the future. So the water cycle is, of course, very important and will change. If that changes, the ecosystems are strongly affected. So this is almost all the prelude on climate change, as I think you do have a lot of background on that. And usually then I like to show also at this point this graph. It's a Mediterranean plant, rosemary. And why do I show it? I show it because I really like it. I like to cook with it. But I particularly show it because it's pretty hard to grow that in Jena. And it's not so, it's the reason for that is not that we don't have the right mean average temperature, or the annual precipitation wouldn't be all right. But it is actually more related to the fact that every couple of years, this year was, for example, one, we have minus 20 degrees with a Siberian and polar cold entering the continental climate of Jena, and then it's too cold. So a single day of minus 20 or 25 degrees can actually kill this plant. That's a problem. So what is really the point is here that for life, ecosystems, but also for societies, what matters is not really the average average temperature or average precipitation. We have seen that, unfortunately, right now in Germany, how important and how devastating extreme events can be, where we have 200 millimeters of rain on one day, which is the amount that usually falls in 2 months. And maybe the annual rainfall, let's see, in Western Germany will not be so different. But this single event causes the problems. And in this sense, to my mind, the sustainability goals, sustainable development goals relate actually to climate extremes like the rosemary relates to it. That climate extremes can really endanger the pathway towards sustainable development goals by single shocks that set us back. Again, we have a good example that's not related to climate, but related to the pandemic, which was also an extreme event, or is an extreme event, where if you look at the trajectories, for example, of the poverty, let's take SDG 1, the goal has been approached with declining poverty, but now basically with the pandemic, actually the indices go bad again. On the other hand, it is important to note that reaching towards sustainable development goals also strengthens the resilience against climate extremes. So if we have less poverty, more education, better equality of different groups, gender or minorities, then we will also have a better chance that people have the power to react to extreme events. For example, they are informed, they can interpret it, and they are also mobile enough, for example. It's actually similar to the rosemary. If it grows big enough, it has also enough resources to resprout, for example, after such a killing event. So it is not so different. Overall, if we talk about this effect of climate extremes, even it has not been really so much considered really in the Sustainable Development Goals discussion itself. If you look at the documents, and the urgency of this is really undoubted. The World Economic Forum is presenting annually since a couple of years a global risk report, and you see here that extreme weather has been on the second or first rank 2015, 16, 17, 18, 19, and in fact also 20. And in 20, actually, you see that all the environmental risks that you see here, all in green, have been actually ranked on the first top likely events that incur global risks. 2021 just came out now. Still, these environmental risks are on the top, but of course, these things are also related to perception the pandemic has, or infectious diseases overall have become, of course, have gotten more attention also. The real critical thing, for example, if you think about hazards, natural hazards, with climate extremes compared, for example, to earthquakes, is that we are having here a moving target because we have this changing climate. Here's just a summary from a couple of studies by Schirmer, actually, where we actually see that, for example, heat waves and droughts are more severe or more likely to occur through climate change. So rules and norms that we had before may not be valid anymore because basically the system is non-stationary and is changing. That's what I mean here with a moving target. So that's why this changing magnitude and frequency imposes stronger challenges than, for example, other natural hazards like what I meant, earthquakes, for example. Another complication which really relates to the systemic nature of systems, of ecosystems, and the effect of extremes is really that we can have a compound and cascading event that actually then act in synergy. Here, just two examples. On the top, for example, we had these forest fires in Southern California, which opened the soil, and then a couple of months later, heavy rain that then caused these mud floods because the soil was open and couldn't be held together by the forest. And only through the combination of this, we had this devastating mud flood there. Or another example, a bit more complex, is related to fire that we see so in California, but also elsewhere. We have this wet winter, we get dense vegetation, that means a lot of burnable fuel, then a dry and hot summer where the vegetation dries out. On top of that, very strong wind, and only this combination then led to these catastrophic fires that are rare, but that are then extremely hard to protect against. And that these two examples are from one of the richest areas of the world, also shows you that also the richest countries and areas are not are threatened by these events. And another example that we have also looked a bit with remote sensing data and some analysis. It's a Russian heat wave where we can also see this cascading effect that go really beyond sectors or go across sectors and even go across borders. So, I mean, the whole thing basically started with this typical omega situation where we have a very stable high, which sits there for a couple of weeks, and that on top of the climate change. That leads to heat wave and drought in that area. That leads to vegetation stress in the ecosystems, drying out of vegetation, which makes forest fires more likely, which then actually affect the air chemistry, the regional air chemistry by air pollution with nitrous oxides, but also fine particles. And actually only the combination of this effect, this pathway, this causal pathway towards the air pollution with a direct effect of heat wave then cause, for example, the high mortality that we unfortunately had seen in particular in Moscow, but also surrounding areas. So this is really important that there are several causal pathways coming together. And there's another one that goes towards socioeconomic system that goes via agriculture with failed harvests, in particular the wheat. A lot of reduction of wheat harvest that then leads to volatility and increase of the wheat prices on the global commodity markets, together with other factors for sure. Which then this is probably a bit more speculative, but that can then at least be a risk multiplier for social instability in areas where these wheat prices have profound impact on local and household economy, like in the Arab Spring. So there are at least indications that there are links. Of course, it's not a single and monocausal relationship, but I think it's fair to say that these kind of effects can aggravate the risk. So overall, it's really important to have this system view on extreme events where we have the atmosphere and geosphere, the biosphere often as a mediator of those effects, and then the anthroposphere where we feel basically the impact, and where we also have to clearly say that both locally and globally, of course, and there are also feedbacks from the atmosphere to the biosphere and back to the atmosphere and geosphere. This is long-term climate effects, of course, of our emissions, but also short-term effects like regional feedbacks of cooling and warming depending on land use and so on and so forth. Couple of things to consider here: time scales, spatial scales, but also social science aspect like perception of the extremes, valuation and beliefs, if you think about how people react also actually to those extreme events. These kind of system interactions, and I think that's my second last slide on that realm, also incur really counterintuitive effects. I think that's quite important. So things that one would not expect necessarily. One example is the cold extremes. So it's getting warmer, so people will say, and it's also written in some of the IPCC reports, we have less frost days, less cold events. But is that really true? It's actually a bit misleading to say that, because we have this system interactions where biological aspects play a role. And we had an example in Central Europe, particularly in France and Southwest Germany this year, where we had a lot of frost damage in late April, beginning of May, it was more mid-April actually, where we had a relatively warm days in March. So the vegetation could advance, could build their buds for flowering, in particular the vine. And then after the vegetation has developed quite well, then there's this late frost event. And that caused actually quite a problem in the wine industry, in particular in France. So it was really called a calamité agricole, so really a real catastrophe from the ministry. And the reason for that is exactly this interaction between biology, as I tried to explain already, and actually the climate attribution community actually found that such a late frost event has actually become much more likely through climate change, because the warming in this sense and the advance of the vegetation development is faster, if you want, than the delay of the frost days. Another example that is a bit more positive and shows where we can take advantage of these system interactions and as a society also react is work from the group around Moura in Belgium. They looked at East Africa and the relation of wasting among children with drought. And from a natural science perspective, you would say, well, the stronger the drought, you have less harvest, less water. So you would have an increase in this malnutrition of children. But what you see here empirically, it is actually the largest effect with moderate drought. And so I cannot prove this, but my hypothesis actually is that we do have these interactions here, where this would be the normal causal pathway: drought severity, malnutrition, and then wasting or even mortality. But on the other hand, if we have stronger drought severity, that will also increase the risk perception through indices, through media, and this will initiate possible help, both awareness and help, both nationally but also internationally. And this can then have actually an effect, a stabilizing effect. So more help means less malnutrition, or more help means less mortality. That's how to read the plus and minus. And then basically lead to a mitigation of these effects. So these are the systemic effects. And again, I was mentioning the World Economic Forum in a very abstract and global sense. They also recognize that part of the problem are really the global systemic risks, where actually extreme weather, climate action failure builds here for example, a triangle with the water crisis, a strong one, and where then we have links to more social science related risk, where this can lead to social instability, can lead to national and global governance failure, to even state collapse and involuntary migration, which we have also seen. Again, the causal links are not 100% established, but it's plausible. And this is also why a kind of, let's say, attitude, for example, in Germany, climate change won't be too difficult for us, we can adapt, is neglecting that we have these global effects, and which could, for example, cause migration, but also instability in other areas, which then, through global economic links, will also affect Germany very strongly. So it would be very naive to look at a country in a singular way only. So these are systemic risk, and these interactions between these hazards and socioeconomic factors can be also seen from these very simple statistics, that almost 2/3 of the deaths from natural hazard-related disasters actually occur in the top 30 fragile states. So there's these strong interactions of vulnerability. And I think, so climate is, of course, a very important aspect, but I just showed that very quickly. I think it's also surely known to many of you is the Anthropocene, the great acceleration. Climate change is actually only one aspect of our environmental changes, which also relate to land use, biodiversity loss, ecosystem degradation, and water use, and so on and so forth. I think we should keep that in mind. Interesting thing that I found the other day is a publication from last year. I don't know if you have seen that, but basically we are crossing actually a certain threshold, or we have crossed a certain threshold that can be summarized, or has been summarized here in a German popular science journal. We have more concrete than biomass since the last year. And for example, we have more plastic than animals, or we have more building and infrastructure than trees and shrubs globally. I found that quite striking. And that all basically says that while I think it's good to put the Sustainable Development Goals in the center, because it really links the different challenges together. They cannot be viewed without considering climate change, because it's such a big and global kind of challenge that will change the conditions everywhere. And on the other hand, we cannot ignore climate. We cannot ignore disaster risk, which are basically treated in the Sendai framework. And so I think we have to move from simple sustainable development to risk-aware sustainable development. And there are also things happening. Just let you know, the German has a strategy on sustainability, which was quite advanced already 2018. There was nothing about this. In climate extremes was only mentioned 3 times and only in one resort in a 200-page strategy document. Disasters only 1 time. Risks 8 times, but really with inconsistent meanings. But there has been a process of communication also on that, related actually, or triggered by the pandemic. And we have actually now an update 2021, and that has already much improved. And I think we scientists have actually also the responsibility to raise this awareness. I think I'm a bit slow. I skip this slide, which is on systemic risk modeling. If there are any questions, keep it in mind. Just let me know afterwards. I think I will also only quickly address this. It's more like an advertisement, well, there's a paper that you can read where we wrote a bit about it in a more commentary style. You see that on the left-hand side. On the right-hand side, our RiskCan. If you Google it, RiskCan, you will find it. Feel free actually to join it if you're interested in these questions. We will actually have a call for a new steering committee this year, and also for membership that every day basically. So feel free to get in contact with us. Also with different working groups that are all related to the different topics, but always connected to systemic risk. But now I want to go towards the role of data science and artificial intelligence. And here one important point that we, I think, as a geoscientist have been realizing in the past years is that there's probably has been much too much emphasis of AI and machine learning for Amazon and Netflix and so on, and, image recognition, and while at the same time these classical machine learning tasks like object classification, dogs and cats, or super resolution and fusion, trying to increase the resolution of images, reconstruct them, have their direct analogs in our earth science. Modeling and prediction, for example, for pattern classification of hurricanes or atmospheric rivers or droughts, or also for statistical downscaling of these quite coarse scale climate and weather predictions from, let's say, a couple of kilometers, typically 50-kilometer grid boxes, to really what's going on in your garden if you want. So this is more the static view, and then we have a more dynamic view, which is a very active field also in machine learning, trying to predict actually how a video will develop. Like here, seen people moving through the scene, or for autonomous driving. It's of course important to predict what's going on in the future, and that directly relates to short-term forecasting, or for example, temperature or precipitation, or also the impacts. So it's kind of forecasting, dynamic forecasting in time, and also language translation, where AI has made big contributions, directly relates actually to dynamic time series for modeling, where the past and the context, for example, what has been said in the past determines what will happen in the future, and these kind of things can be learned. And this is similar, like for example, for disturbances in ecosystems, where the time series modeling will then also benefit from these kind of approaches. Concretely, for disaster risk reduction from natural hazards like climate extremes, there has been actually a lot of work meanwhile on AI. I think the emphasis is a bit, or started at least, with more focus on the response and recovery. So once a disaster has happened, aerial photographs, satellite images can be quickly analyzed, damages assessed, and then this helps and a lot of information for first aid and humanitarian actors, and but also for before a disaster to create preparedness or to mitigate already potential disasters by anticipation. Artificial intelligence is playing more and more important role, and I think that is actually a really important field, because preparedness is of course always better than response in a way. And I see actually at least 3 domains of machine learning where it can play a role. On the one, it is understanding the causes and conditions for impacts and disasters, for example, from climate extremes. So kind of forensic analysis of past impacts. The prediction and forecast of concrete impacts, which actually overcomes the limitations of weather-only based approaches. So weather forecasts are already in place to predict the droughts or floods, but it's often just the weather, and it doesn't tell us how actually a certain weather event will then actually translate into very local impacts. So this can be done by looking at what is happening on the land surface. And since physical models are not so easy to do with biological systems, this is often a field where AI can contribute a lot. So it's about localization, local effects, but also looking into impacts that can be not modeled very easily in a physical way. And last but not least, often overlooked is really, I think, also it can be a tool for communication. And I will have one example here that shows the visualization. Just one example from our own work, where you can basically see that with the wealth of observations, for example, Earth observation from space, we have a lot of different variables that are simultaneously observed, that we can store in these space-time cubes, in these, we call them Earth system data cubes, and then we can analyze them and see if there are strange situations, and we can also try to see if we can anticipate strange multivariate situations. Here's a kind of proof of concept where we just looked at all these data and looked at these space-time areas, so these voxels in the year of 2010, and then these orange parts are the areas where there were extreme events going on, anomalies going on, and what, for example, one detects is the well-known already Russian heat wave that I already talked about. But we found that basically without any theoretical or prescribed information. Of course, this one is also easy to find. It was just very hot, but it's actually very interesting. If you then look at the response again at the impact, then we do actually see that the impact is quite heterogeneous. So the heat wave was quite homogeneous, but the impact was quite heterogeneous, as you can see on the right-hand side, with a strong negative impact on productivity here in red on the lower side in the southern areas, and actually more positive impact in the northern area. Then the next question is, okay, is this just for the Russian heat wave? And but what we actually see here, by objectively analyzing all these extreme events globally, we see that we have a lot of blue spots also where anomalous situations actually do not lead to very negative impacts all the time. And the question is, of course, now, when do we expect very negative impacts, where we need to be prepared, and where not, and when not? And this is exactly where machine learning can, of course, help in analyzing, and where maybe humans are, without machine learning, are a bit limited. One can, for example, make a plot. We look temperature, moisture on the X and Y axis, and then we look at the impact here with the colors, and you can see, yeah, there's a little bit more effect when it's drier. There are more red spots, but there are also blue spots in the upper right and the upper left corner. So this doesn't separate everything so well. And if we employ a machine learning method, with some explainable AI elements without going into all the details. We actually see here which factors actually play a role and in which direction also, and show that actually land cover vegetation plays an important role, whether we have negative or positive effects. Forests actually react on a short term rather positively to most of these extremes, but also relates to the growing season temperature that we have seen in the previous plot, but also to something like the duration of the extreme event. So longer event basically means also higher dose, if you want, of the stress. That makes sense. Brings then more negative effects. Yeah, let me also skip that one. That shows something similar for societal impact, but I think I should, in the interest of time, skip that. Maybe just here also the point, one can also look at macroeconomic data from states, but even better if you have regional information. That's a bit the limiting factor here. But where we can basically summarize all these macroeconomic indicators into some dimensions that give us then the indication in which direction a state or region actually develops, and actually how it also recovers from after extreme event, for example, and bringing all of these different states together can possibly also help us to understand how societies can be resilient. Basically, learning from the past here. Yeah, I'm coming to the second point: prediction forecast of impact. This has been realized for resilience that this is a very important aspect. Particularly, the humanitarians have seen that forecast-based anticipatory early action is it called. So basically, the idea is if there's a certain risk that in a certain area there will be a drought or a flood in the future, in the next month or so, then the humanitarians can already invest a little bit of money, like sending a couple of people for 20,000 euro or so into the area, prepare the people, talk to the mayors and to the governments, so that they can be prepared. And then basically by this preparation, the damage is mitigated. And some calculations indicate that actually the return of investment is basically $3 per dollar invested by this forecast-based financing. So this is really important. And so far it is, again, it's mostly the weather services who interact here. And with AI, again, it is, I think one can probably, if one can even get predictions of what are the anticipated impacts, that would be even better. And this is, again, where some AI research, actually another example of our own, can hopefully help. Here's just an example that relates to the super resolution thing that I showed at the beginning. The question is basically here, can we predict from core scale predictors like mean climate, precipitation, some overall land use map, some geological map, can we predict with a machine learning approach how the landscape probably looks like from space? And this is basically the idea. What's seen on the left-hand side goes in, what's seen on the right-hand side should be coming out, and it should be similar to what we see real. So there's a downscaling, if you want, of the drivers of the metrology, that is only core scale, but also of the impacts. And if you're close to a lake, your impacts of a drought might be lower because you have access to groundwater and so on and so forth. All these factors should be kind of learned by the system. And we have one study that looks into the spatial prediction of the landscapes at the sentinel resolution at 20 meters. I found that really amazing, that it is indeed possible. One of those rows is the machine learned prediction, and one of those rows is actually the real ground truth in the test case. These are good examples. There are also worse examples, but I can't differentiate them now. So the upper one is the predicted, the lower one is the observed. They are still different, and that's also okay because it's just a possible generation of a possible landscape. But you see that, and we can see that the statistics, the statistics actually resemble to the spatial statistics with this machine learning approach, the real landscape. And this actually, again, using an algorithm, adapting it, that has been used to convert drawings, line drawings that you see on the left-hand side, into full images on the right-hand side. And I believe this application that I just showed has maybe more sustainable development goal relevant impacts and potential than this toy example with the handbags. And the next step is actually not to predict average landscapes, but also do dynamic local impact forecasting. Actually, that will happen an EU project in Africa. And the idea is basically that we start with the synoptic situation and the coarse scale weather and try to predict the fine scale impact by incorporating the local geo factors and by trying to understand with a machine learning approach what are the local factors that then cause the impact, like slope, aspect, closeness to river, and these kind of things. And then also in the second step, also look at the long-term consequences and try to understand when a forest or so is actually resilient or is strongly affected, on the other hand, after such an event. So kind of memory effects. And this is maybe a bit more technical, but basically this is how these kind of things look like. We have a set of variables that go in time, states that are kind of intrinsically modeled, latent states with a machine learning model. This is this H here. And then okay, the actually the drivers here on the lower side, and then on the upper side we have basically from the states and the drivers we can then get these local impacts and how they develop in time. And again, this is only possible because we have this great Earth observation now. Here's an example, almost real time at that time, from the drought effects 2018 in Europe, where you see within a month basically the northwestern Europe turned from green to brown. There's a challenge out, and if any machine learning person is interested, go to this challenge, and maybe you have a good algorithm actually to tackle this quite challenging problem of dynamic impact forecasting at this very local scale. So last thing that I want to highlight, it's certainly a bit outside my own research, but it's, I think, important if you talk about disaster risk reduction in general, is the communication. All the science and good predictions don't help if the warnings don't work, and we have seen that just right now in Germany with the floods. And basically, if you think about the early warning chain, actually, colleague Brian Golding has made this very nice sketch here with a so-called 5 valleys of death. It's a chain, and if any part of the chain breaks, the decision will not be the right decision. So we need good observations. We need good forecasts. We need a good hazard forecast and impact forecast. So that's more or less what I talked about so far. But then we also need a good warning, good communication of the warning, and of course a decision. And then that's where, of course, communication science, behavioral psychology, and also socio-economic modeling overall play an important role. And one can argue that machine learning possibly plays a more and more important role in those realms where theoretical and physical modeling is even less simple. But I want to make just simply a point for communication. A work from the group of Benjo, one of the third of the leaders in artificial intelligence, is this one, where which basically shows that artificial intelligence can also generate images, imagine images, and you can basically give the algorithm a picture, like on the left-hand side, and say, how would it look like with a flood? Of course, we have trained it with other examples before, but then basically this algorithm can then basically generate this image on the right-hand side, and that probably overall offers a better warning than something like, oh, there will be 200 millimeters of rain, because it's easier to grasp for people that are not usually counting with millimeters of rain every day. Yeah, let me skip that also, but just a word of caution, if you want. There has been also a pretty nice review on the overall AI impacts on sustainable development goals and reaching them. I showed you some opportunities, I think, that are more coming from the perspective of understanding, prediction, and generation of possible futures or communication. And you see also this review shows a lot of positive impacts, but there are also possible negative impacts of AI when we think about reaching sustainable development goals. And these are typical, also very current challenges of AI now, like one can have biased predictions. If you learn something just on, let's say, where you have a lot of data, let's say in Europe, and then you want to apply that simply to Asia or South America or Africa, where maybe there's less data, then there can be a lot of biases that will actually give you the wrong decision basis. There can be actually increased inequality between and within countries because there's different level of infrastructure that's needed to perform these methods. It can also lead, is related to the first point, but more the societal point, can lead to increased discrimination and stereotypes that are learned with this machine learning approaches. And if it's very centralized in big centers, then this can also lead actually to less resilience, because if these centers are affected, then everything is gone, if you want. And this is certainly very important, to be taken very serious. And it is also quite an active and important field in AI. It's called fair AI, to avoid these biases, inequalities. Also explainable AI, to understand and not blindly follow the recommendations. And overall, there's of course also a big new developing field of ethics in AI, which relates to data protection and so on and so forth. So just to make this point, I'm not an expert really in this, but I think it's an important point to consider. So the take-home message, or the few messages, is if we talk about the climate extremes, I hope I could convince you that really climate extremes matter, not only the mean temperatures, as they are often conveyed in short messages, and in particular hydrometeorological extremes, droughts, and floods are, I think, the ones that will probably impact and shape ecosystems and societies in the future much more strongly than the temperature per se. It is really important to consider systemic effects, cascades, and compounds, and they because they matter a lot, and at the same time they are hard to model. So there are often no simple solutions, or simple solutions might ignore the systemic effects. So this is a really strong both scientific and societal challenge, I think. And while last but not least, it's really the point that there's, I think, a big potential for AI. It can help in many aspects. I hope I showed you some examples, more of basic research. But I think it's really important to consider the drawbacks, the potential pitfalls, and handle it with care. So in this sense, thanks for your attention. I'm looking forward to the discussion.
Thank you very much, Markus, for this excellent talk. And I think this was a really great way to end this series of seminars, because you bring both the science and the societal aspect related to sustainability. And I have a few questions, but I would like to give the floor to the participants, both those on Zoom or those watching on YouTube. Those watching on YouTube, you can just paste your question in the chat, please. And those on Zoom, you can raise your hands, your icon raising hand, because I don't see all your faces. Unless you cannot find, then you can just chime in and unmute yourself. So, do we have any questions? I'm going to check the YouTube. Okay, so I think people are still trying to fill comfortable, I'm gonna now tell my students, if they're the ones that are here watching, that they should, even though this doesn't count for the grade anymore, but you should chime in and ask something. And Markus, then I'm very surprised. I was very shocked actually with that threshold you mentioned about that we overcome the amount of biomass with cement. So this was last year? That's what you mentioned.
Yeah, the study from last year from colleagues from the Weizmann Institute, and it's really just a counting approach, but it's
of course
it's interesting, and I found it also quite shocking.
It's shocking, yeah. More than interesting, it's really
it's of course more of a metaphor, but it's symbolic, I think, to some extent. Yeah.
That's right. That's what I was gonna say, is the symbolic aspect that is a little bit troublesome. We have a question from Ladislav. Go ahead and unmute yourself. You can ask your question.
You need to unmute.
Oh, works now?
Yes.
Thank you.
Yes.
Thank you very much for a nice presentation. My question would be, because recently there was so many extreme events, and we know that we are heading towards even warmer world. Is it possible somehow? Do you see the way to use the artificial intelligence also to give us a peek into how this, for example, +2 degrees world could look like, and extent of these events? Because a lot of the discussion was about the short forecasting. Would you also have some opinion on this, or?
Yeah, actually, I skipped one slide, and I can share it again, where I alluded to this. So actually, talking more about impact here, actually, and less on the extremes themselves, but I think it's a similar argument. So one can actually do it, and actually Chris, that you know, did it actually in his study. So he was predicting the landscape from the climate conditions, and then one can say, okay, what happens if the temperature increases or the precipitation changes? And you see here, I think it started here. This was the original one. You can see here, if it's getting warmer, the snow disappears. If it's getting drier, it's getting more from these more greenish, reddish colors to more yellowish colors. So it's kind of a plausible thing that we get. So we basically get something. We can do it, but one has to be really, really careful, because it is really, at the end, these are statistical methods, and at the end, if we go for climate change, we want to know what's in 50 years, 100 years. It is an extrapolation, and for example, here we cannot account for CO2 effects on vegetation that might change the whole picture, also other effects, and so I think it is, one has to be very very cautious when doing that, and a possible solution to that, I believe, is actually combining artificial intelligence with more theoretically theory or science or physically based modeling, where the physically based modeling can basically give you, if you want, the handrail that you are realistic, or that your extrapolations are physically meaningful. And then if you think that you are still within the right domain of effects, then these artificial intelligence methods can maybe give you additional information. But one always has to be careful that such an approach will always have difficulties in extrapolating, because at the end it's a statistical method.
Thanks a lot.
Thank you both. Do we have any more questions? This is your opportunity. I think the students that were in Ecoliteracy, I don't know if you remember, but I have actually shown a little video of that data cube, because I do think it's a fantastic visualization tool of the climate extremes. Markus, so actually, I don't know if you want to comment on this, but we've all watched a little bit in horror as that the floods happened there in Germany. I bet this was also surprising in a way for you, but I actually wanted, if you don't mind, to comment a little bit more on that, on how, because then I heard that there were some warnings and somehow it failed in preparing people or reaching people. Do you want to just elaborate a little bit more on that so we know? And also, where do you think, I mean, you mentioned a little bit of this, but where AI actually can help in these situations?
Yeah, I mean, I don't know more than what is also in the press. Yeah, but it seems really indeed the case, and maybe some of the other Germans can actually chime in if they have read more about it already. But it seems to be indeed the case that both at European level and at German national level, so the German Weather Service and at this European EFIS, or this German European, I don't remember now the exact name, information system, they both issue the warnings. And these are general warnings that are natural, science-based. And then we are a federal state with different federal states. And then we have the Landkreise, I don't know, the districts and so on, and then the communities. And I think the different they reacted actually differently to that. And some did warn, others didn't warn so well. And it is really a matter of psychology. I mean, it is amazing. I mean, there are examples of buildings that are standing, have been standing like bills, and those standing since the 1700s. Mm-hmm. And this mill was standing there, survived 2 world wars, and also all the weather that's going on. And so nobody can imagine that. And I think going beyond that, even 200 millimeters will come, yeah, but it will not come here. And it never happened here. So the experience that people have is, I think, so strong. I mean, this is just my layman psychological interpretation, but also talking to people like Brian Golding from UK, and he works a lot on this early warning. He's basically saying the same, and this is his values of death thing that he's stressing, and he says the same, that often this is then the bottleneck to activate the people, and that's where AI, with this kind of more as a communication tool, I think has a role, but also for a better localization of impact. So if one could basically say, well, this village is particularly threatened, and you can do that not with a metrology. You can only do that if you have the other geofactor. So that's where the geoecology comes into play. There's actually an example that was also in the German news. There were the same rain amounts in northeastern Germany just a couple of weeks or months ago in the Uckermark. So you are the Portuguese don't know, but it's basically Pommern. Not much happened. A couple of cellars went with water, but not much happened, just because the landscape looks so differently there. And then these kind of things, I think we also still have this too strong of a disconnect between actually the weather people and the ecologists, and also of course the ecological process at landscape scale. They are so complex. They are so much biology driven. They cannot be described with Navier-Stokes and thermodynamics only. We need a lot of parameters that are unknown and so on. And that's where I think actually AI can help support the modeling of the reactions on a more local scale, where physical modeling is basically not feasible, I would argue, at least at this point, still not feasible.
Thanks. Yeah, it looks like there's still a lot to be done, and communication is also essential between these fields, as you say, right? And when we're looking at when we're in our bubble of the natural or earth sciences, things even seem a little bit more practical, even though you do know from your work that even when you put in the biosphere in the mix of everything else, and as I often remarked in the seminars there, right? I was also, but that's not a conifer, or that's not a angiosperm. It already throws things out of whack. But when you include people and behavior and society, it also becomes more complex. But I think this was really excellent to bring about all those topics. And I will leave a last minute chance for people to comment or ask a question. And if you don't know how to raise the little hand icon, because that happened in the past, just chime in, unmute yourself, and say something. And if not, I would like to thank you, Markus, very, very much for this interesting talk. And I wish you all the luck in keeping your contributions in this field, both in developing better the models, but also on your part of reaching out as a scientist. As you say, I think it's very important that science participate in the awareness and the solutions and in sustainable development.
Yeah, thanks. It was a pleasure to talk and to discuss. Thanks for the questions also.
Thank you. Welcome. Okay, thank you, everyone. This was the last webinar of the Science and Society for Sustainability series. If you have followed the others, you can also go to the UNESCO Chair on Biodiversity Safeguard for Sustainable Development of the University of Coimbra website and see the list of the webinars. And if you thought these were interesting, send an email to the chair email address requesting us to continue this in the next academic year. Thank you again, Markus. Thank you again to all the participants, and I see you all sometime soon.
Bye.